Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What would you do with a brain if you had one?
Do? Why, if I had a brain, I could...
Miles per hour.
I could while away
46, 56 degrees.
All right, thank you very much. Feels strange, I can't see any faces. So my name is James Butler. I teach physics at Pacific University. I've never been wired so much for a talk before. I feel like they have my EKG and everything going on here. And I've never given a talk on this big of a screen before. Like, it's just massive. We need to get one of these at Pacific. So I teach undergrads at Pacific. I know there's a contingent of undergrads from Pacific here, so shout out to you guys. All right. And I also teach in the College of Optometry at Pacific, and I heard there's some optometry for students from Pacific here too. Is that right? All right, excellent, cool. Very good, so thank you all for coming and supporting. I am not a cosmologist or anything like that. My research specialty is actually in optics, historically, but I do teach an undergraduate course in relativity, and relativity for me is really what inspired me to go into physics and what sort of helped me grow my passion for physics from an early age was that. And I grew up going to OMSI. I remember going to OMSI back over when it was by the zoo. So it's really an honor for me to be here giving a talk about relativity in this forum. So I'm going to be talking about cause effect and the physics of time. And I'm going to say that Einstein was not a fruitcake. So if anybody seen this movie before, 12 Monkeys? Yeah, so it's a great movie. Brad Pitt, he's probably one of my favorite characters in the movie. So he at one point says that Einstein was a fruitcake in the movie, and I'm claiming he's not, even though this picture might say otherwise. So I'm gonna have to be able to be over here to be able to see. Let's see. So I'm going to first talk about. Let's see. Can I get out of this mode for a second? I want to swap this so I can see. Well, I'll just be here. That's fine. So I want to first talk about 12 Monkeys, and actually we'll talk about the movie a little bit, and sort of prepare you for things to think about that I'm going to talk about in my talk that I want you to think about in the context of the movie. So we hold very tightly to this concept of causality, where causes have to precede effects, right? So if I push like this the button on my laser pointer, that has to happen before you see the green light appear on the screen, right? And it's really this idea of causality that cause precedes effect that's in relativity very closely related to this idea of why no information can travel faster than the speed of light. Right? But perhaps time travel maybe is permitted. I'm thinking of time travel as backward time travel. Maybe that's permitted if somehow you have sort of a self-consistency requirement, right? That maybe that what we call future events might be able to, say future events might be able to affect past events in some way as long as that there's a self-consistency, right? So, and what would this mean for free will? Like, for example, what if you were able to go back in time and you want to stop your young self from growing old and then growing old and going back in time to in the first place, right? So would nature do something to stop me from being able to do that? Right, so in this talk, I'm going to talk about, is time travel really possible, right? So, well, in a sense, we are, right? So we're all traveling forward through time right now, right? Of course, as we sit here earlier today, you were in class, you were at work, whatever it was, right? And now you're here at the talk, and a little bit later, you're going to be watching the movie. So we're all moving forward in time, and we assume that we're all moving forward in time at the same rate, right? That all of our clocks are all ticking at the same way, right? And in fact, we can think of that as one of nature's fundamental commands, that everything must move onward through time, right? We could call it time travel, in a sense, right? If somehow our clocks ticked off different amounts of time between the same two events, right? So if you had two people leave to come here to OMSI tonight, and you both left in different cars, and you arrived here at the same you arrived at what apparently was at the same time, and you both looked at your wristwatches, and you both maybe had observed different amounts of time go by on the same and your wristwatches, so that your clocks were running in some way differently. we could call that time travel, even though you were going forward in time, that you would say one person aged more than the other or something like that. So for now, I'm going to focus on this sort of forward time travel before we talk about backward time travel and what that might mean. Right? So physics is all about quantifying, right? Coming up with mathematical models to quantify the universe around us and observations. So we want to quantify time and space itself when we talk about relativity. So the fundamental thing is the idea of an event. So events are any localized physical phenomenon that requires a position and a time to be able to say what it is, right, to characterize it. So like this talk right now is an event, right? We can say it's happening at one specific place, the address of OMSI. It's happening at a specific time, right? So that is an event. And in some sense, we think of those events, all physical events, as the building blocks of the universe, right? Everything is made of these events, these physical occurrences. So for example, maybe this is me standing here saying hello, right? That would be an event. Okay? And we want to start quantifying that. So the way we quantify it, we want to start talking about where and when did that event take place. So to do that, in the simplest, most direct way possible, is to set up a grid of meter sticks and clocks to do that. And that's what, so it's down here, folks can maybe see it. What I have down here, just as a help as a visual aid, is a set of meter sticks and clocks. So at every intersection, we have a little stopwatch, and that those are all presumably synchronized, right? So they're all ticking away at the same rate, at the same time. And so what we're going to do is for every event that happens, we're going to go to our grid. If we imagine this grid extending everywhere, and say wherever event that was, we go to the nearest clock, and we write down what position I'm at and what time was on that clock. So right here, maybe I say hello. I'm standing right here. This is the origin of my grid. This way is, say, east and north, even if it's not really east and north. Right? And I look at this clock, and maybe at this clock it reads 10:10 a.m. when I do that. So I write that down for filing for later, right? For later analysis. 10:10 a.m. I'm here. And then maybe a little bit later, I'm over here now, right? And I say hello again. Right? So now I'm at maybe 2 meters over and 1 meter up this way, right? So 2 meters east, 1 meter north, and I read the clock now, and now it's 10:30 a.m., right? So those are two different events, and I register that for later analysis, right? And so then what we do is we can imagine taking pictures of those two events, right? Those two snapshots of those two events, and we tile them, we stack them on top of each other to give us a sense of the time, the progression through time, right? So down here is my first event, down here my grid, and then above that, in this sort of what we normally think of as a spatial direction, we're going to use the upward direction here, right, as how much time has passed between those events. So at first over here at this time, I'm at 10:10 a.m. I'm saying hello, and then up here at this time, if I go over on this axis, then it's 10:30 a.m. and I'm saying hello again, right? So this vertical axis we use as indicating time, right? And so then the sequence of events throughout my entire life, right, no matter what they are. So this is my interesting life. I go around saying hello all the time, right? So I'm here and I say hello, and I'm over here and I say hello, and I'm here and I say hello. So I keep saying this over and over again. But notice that the way to read this graph, oopsie, go back. The way to read this graph is that here I'm at the lowest value over here. I'm at the smallest time, and this is where I'm at when this event happens. Then when I'm up here, I'm at a different time later, and I'm at a different position, saying hello again. And way up here, I'm at a different position and at a later time. So we string together all these things, and we call this sort of line of events throughout my life my world line. Right? That kind of describes all the events that ever will happen to me throughout my life. Right? So I'm going to periodically throughout the talk, I'm going to sort of take a step back and remind us what we've discovered, or some important points so far. So one is that time and distance of events are quantified using a lattice of meter sticks and clocks, right, is the most fundamental way to do that. And that time itself can be thought of as a directed axis, just like north and east are directed axes. We can think of time in the same way. All right? So, and for now, we're going to assume that our grid is flat. We're going to think about our grid as being a flat space-time, right? So for now, and we're going to assume that the grid that we have, like this grid down here, conforms to the geometry of space itself, right? So that we think of this as completely a flat grid. Flat meaning that if I measure distances and use geometry, normal Euclidean geometry, that all works the way that we think it should in this flat grid. All right, and for now, we're also going to assume that the time axis is also flat. It's not curved in some way. So all three of my axes are flat. right? So in this flat space-time geometry, we can start asking about comparing events for different observers, right? So imagine, let's look at Alice and Bob who are throwing a ball, right? So Alice is going to throw this ball to Bob. And so they're standing here, Alice is standing at some position, and notice that she's standing still. So even though she's stationary, she always stays at the same sort of east position. She's still moving forward through time vertically, right? And same thing for Bob. He's standing still at a different position on east, but he's still moving through time vertically this way. And she throws a ball, and the ball is moving straight this way towards him. But again, we have to look at snapshots, right? So she releases the ball here. A little bit later, the ball is closer to Bob, and a little bit later, the ball is closer to Bob, and a little bit later, he catches it over here, right? And so the ball is changing position and time as it moves forward. And we could ask then, I'm used to going over my computer to have to do that. We could ask, what's the time that each of those would measure between those two events, the events of Alice releasing or throwing the ball and Bob catching the ball. And so we could look over here and say, well, here's this vertical axis represents the time, so this right here, this distance represents how much time it would take. So 5 seconds, let's say, is the time between those for Alice. And over here, since it's the same vertical distance, that means it's the same vertical time, because we're using the vertical to represent time. So they each measure 5 seconds. So you get the same amount of time between those two events. Right? So another couple important things to add to our list then, right, is that you are moving onward through time right now. Even if you're not moving, even if you're sitting still stationary right now, you are still moving onward through time. Your world line is still moving up vertically through this time axis, right? And that is, if in flat space-time at least, that if there's two events, if two people both at rest relative to each other and relative to the grid of meter sticks and clocks measure the time between those two events, they're going to get the same value, the same number. Right? So, but what about if we're in a different situation? What about if we're near the Earth's surface? Instead of Alice and Bob being astronauts floating out in deep space, what if we're near the surface of the Earth? And Alice is now up here at the top of this building. Got to go back. Keep pressing the wrong button. There we go. So Alice is up here at the top of a building, and Bob's at the bottom. And notice I've switched my axes on you just because we normally want to think of Alice dropping the ball down to Bob. So I'm going to use this vertical axis as the actual position now, the height of the ball, and we're going to call time this axis instead, right? So I'm going to make that time. So Alice is standing here at the top of the building, and again, she's standing still, so as time goes on, she always stays at the same height, right? I haven't drawn the building. Obviously, she's not hovering in midair, right? But I didn't want to keep crowding it with buildings. And the same thing with Bob. Bob is standing still, so he stays at the same height the whole time. And she releases the ball, and as the ball goes forward in time, so it drops a little bit. So a little bit later, it's here. A little bit later, it's further down. Notice that it's not following a straight line now because the further time goes on, the faster the ball moves, right, as it's falling towards the ground. And so each increment is falling further and further, faster and faster, until Bob catches it over here. Okay. All right. So the question is, are they still going to measure the same time between these two events, right? Between release and catch, are Alice and Bob still going to measure the same thing? If she measures 5, is he also going to measure 5 seconds? Right? And if it's flat space-time, then yes, right? But space-time is not flat near the Earth, near any kind of gravitating object like the Earth, right? So we have to ask ourselves, well, what does that mean that space-time is not flat? What does a non-flat space-time mean? What does curved space-time mean? Right? And so let's first talk about the space part of that. What does curved space mean? Well, we know that, say, for example, the Earth is not flat. The Earth is a ball, right? Is round. And so if our grid, like this, right, this grid of meter sticks and clocks, if I only look at a small region of the Earth like what we're on right now, this is a very small piece of Earth, so it looks flat, right? I can't tell that the Earth is curved, right? But if I made a very huge grid, right, that spanned the entire United States or something, right? Something like here, if I made a big grid of meter sticks and clocks, we'd be able to tell that the Earth is actually curved, right? Those meter sticks would actually curve and conform to the shape of the Earth itself, right? So that's maybe not surprising that the space part of things can be curved. Although we think of the Earth as curved, we actually think of space itself as curved around the Earth, which is a little bit different way of thinking. What about the time axis? Right? So what would it mean for the time axis to be curved? Well, it turns out that the time axis near a gravitating object like the Earth is also curved. So what that means is if I look back at this sort of a picture, like our ball, right? So imagine maybe as a visual aid to the eye again. I know most of you probably can't see my tape up here, but you can imagine, because I'm drawing a three-dimensional thing on a two-dimensional surface. So this, what you have is a sphere, like a ball. And we're going to have the vertical axis, again, be my height, right? What we had Alice on before, and this direction is time. Right? And so if we imagine that that time axis is also on a curved surface like this ball, then now clocks at different heights are going to run at different rates, right? So, and maybe you can start to think about that. Like if you imagine here's Alice and Bob on the building up here initially, and Alice and Bob over here, final, right? And the ball travels over here to reach Bob at the bottom. That Alice is going to measure this amount of time, and Bob is going to measure this amount of time, right? So they're going to measure different amounts of time as you go across there. Right? So, whereas if, and of course, we don't observe this in our everyday life very much, because if we only look at very, very small increments of time on sort of a human scale, like hours or days or whatever, the amount of the difference in time is very, very small. We call it, it looks locally flat. We don't really notice this curvature, but it's there. And if you have a more accurate enough clocks, you can measure it. Right? So if I zoom in on this, again, this is showing this picture, but on a flat surface, then what you see, right, is up here. Again, if Alice is at the top, she drops the ball, and Bob catches it down here. So this distance here along the time axis, that's how long it takes between those two events for Alice. This is how long it takes between those two events for Bob. So they measure different amounts of time along that time axis if the geometry is curved. Okay. And the way this is drawn, that in this geometry shown, Bob would measure a greater amount of time than Alice measures. Right? Which literally means, if that's true, that every clock that Bob has for measuring a time between those will measure a greater amount of time. So literally, Bob ages a different amount. His own internal body clock, all of his biological functions, all those sorts of things are just another ways that we could use those as clocks, just like we can use gears and electrical circuits and things for clocks too. Everything we have for measuring time would be measured for Bob a longer amount of time than Alice, and so those two, when they compare their clocks, we'll actually see that they'll have aged different amounts. One important note here, that this is actually not the correct geometry for space-time near Earth, near the surface of the Earth. I'm using this because it's easier for us to visualize a spherical geometry like a ball. In reality, the actual curvature near the surface of the Earth, it's actually the reverse of this, that actually Alice measures a greater amount of time, Bob measures a smaller amount of time in the actual geometry. But this is just to sort of help us understand how curvature affects the differences in time between events. Right. So another important note, right, that curved space-time, that the measured time between events is not the same, right, even if the two observers are at rest relative to each other and relative to our meter sticks and clocks, right? But that curvature will affect things. All right. So some properties of space-time curvature. Well, Alice and Bob both are still moving forward in time, just at different rates. So they are going to say that they're going to age different amounts compared to each other, right? That literally Alice will have aged a different amount than Bob. What determines this curvature, right, is Einstein's gravitational field equations. So if we know the energy distribution, the energy density, and the mass distribution, the mass density, and the pressure at any point in space, then Einstein's gravitational field equations will describe what the curvature and geometry of space-time should be for that given mass and pressure distribution. Right? So, well, then that begs the question. So if we can curve space-time in all sorts of weird ways, depending on the types of energy and pressure distribution we have, is it possible to curve it in such a way that Bob might actually travel backward in time compared to Alice, instead of them both moving forward in time at different rates? Is it possible for one of them move backward in time relative to the other? Right? So is time travel into the past possible? Right? Because that's really what the movie is going to be about. Like what lots of Hollywood movies are about is traveling backward in time, and so the movie today is going to be all about that too, right? And to think about this, how this comes into play is, imagine, let's go back to Bob standing here at the bottom of the building, right? And let's suppose this was the correct geometry. Like I said, this is not the correct geometry near the Earth, but suppose we could set up this geometry for space-time. And suppose Bob just stood here for forever, right? So poor Bob is just standing here at the bottom of the building, just standing here forever. And he starts standing here, right here. This is the origin, right? So he starts his stopwatch right here at whatever, January 31st, right, at now, at 2017. And he starts waiting. And his world line, right, time is ticking away. So he's going further forward and forward and forward in time. So maybe over here, he's now at a year later. Maybe it's January 31st, 2018. And he still, as he goes around, if this was the correct geometry of space-time, eventually he would come back around here. And all of a sudden, his world line would intersect where it started, right? So at the next moment, his clocks would be back to reading what they were at the very beginning when he started standing here at the beginning. So all of a sudden, it's back to being January 31st, 2017 again, right? So this sort of a world line, one that wraps around and loops back on itself, is given a technical name of a closed time-like curve. And that's sort of central, those sorts of shapes, world lines that wrap around and meet themselves again, are central to the question of whether or not backwards time travel is possible. Okay, so there's been a lot of research into this, not by me, but by many people, about are these closed time-like curves required, right? So the idea is, well, since we know that it's mass and energy and pressure, right, the distribution of those that determine the curvature, can we develop the right distribution that can give us a curvature that would allow this? But we have to remember that just because we can imagine all sorts of different curvatures, all sorts of different ways we can take a ball and squish it around, that doesn't mean that all of those are actually physically possible, right? Not every possible shape is a solution to Einstein's field equations. So folks are looking into this to see, are there possible solutions that allow these closed time-like curves? The good news is that apparently there are solutions. There are possible solutions that allow for this. Right? The bad news is that they typically require what are called exotic materials. And what they mean by that is that they're sort of vacuum regions of space. And a vacuum you normally think of as having essentially nothing in it in some sense, right? That has zero average energy, zero average pressure. But it requires a vacuum that has a negative energy density. So in some sense, that means a negative mass and a negative pressure in this vacuum region of space. Okay? Or these very fast-moving, near the speed of light moving, what are called cosmic strings, which are also hypothetical sort of features in the universe that have never been observed, that are some cosmological models predict them. So if you have those, then it might be possible to create these sort of closed time-like curve geometries. But these sorts of things are difficult, if not impossible, to make. In reality, there's still lots of questions as to whether or not you can make them, and if you can make them, can you make them in sufficient quantities to curve space-time enough to do this? But let's suppose for now that that's not a problem. Let's suppose that we can, right? Let's suppose that that's just an engineering problem to figure out how to make enough of this exotic material. So if you can do that, then you can make what are called wormholes. So some folks may have heard this term wormholes before, right? And so these are sort of theoretical situations where you can, say, curve space-time in such a way that you can connect different features of the universe that you couldn't have before. So imagine back to our ball geometry, right? So what we can imagine is that in a two-dimensional version of us, right, we live in a three-dimensional world with a fourth dimension of time, but imagine instead we lived on a two-dimensional surface. So in our normal space, we're required to live sort of on the surface of this ball, right? And if we're going to go from one place to another on the ball, we have to stay on the surface the whole time, right? And that's sort of like us going from here to wherever. If I go to here to Alpha Centauri, I have to sort of, in a sense, stay on the surface of the ball to get there. Not knowing that if I could somehow, if it's curved, right, if this is a curved geometry, there is a faster way. If I could, somehow tunnel through the middle of the ball to get over there, I could, in a sense, travel a straighter line getting there, and I could get there sooner, right? And that region of space-time, in a sense, that's inaccessible to us, is sometimes called hyperspace. So if you ever heard the term hyperspace, that's the sort of extra dimension of space that our curved space-time is sort of curving into that we have no way of ever accessing. But if I could somehow push the ball in, right, if I could not apply enough pressure, I could force in, I could compress the ball all the way across and sort of make a tunnel through here that was still the surface of the ball, just pushing it in to indent it all the way through, right? That's the sort of idea of a wormhole, that you can indent in the surface of the ball enough on both sides to meet in the middle. And you can make this sort of tunnel where you're still staying on the surface of the ball the whole time, but you're sort of tunneling through the middle of the, utilizing this extra feature of hyperspace that you normally can't access. So for example, if we were able to do this, here's Earth and here's Alpha Centauri, that if we could make a wormhole between these, then maybe here at this particular instant, here's the Earth clocks are at 2017 right now, and here's the Alpha Centauri clocks at 2017, right? And then we could, instead of going from here all the way around through normal space to get there, we could just jump into the wormhole and get here a lot sooner, right? Because we have a lot shorter distance to travel, right? And if you were able to do this, it's theoretically possible then to desynchronize the clocks on Earth and Alpha Centauri, right? And the way you do that is you, in a sense, gravitationally you pull away, you grab onto this side of the wormhole and you accelerate it up to a very high rate of speed, close to the speed of light. You take it out somewhere and you bring it back, right? So we also know from special relativity that if I take something and move it so it goes very close to the speed of light and have it turn around and come back, that if I compare clocks between the people who never left and the people who left on the rocket ship and came back, we'll have measured different amounts of time, and so they will have desynchronized their clocks. So here I can do that. I can accelerate this wormhole back and around and come back at some point later, say a few years later. So after I do that, now the Earth clocks now say 2025, but the Alpha Centauri clocks now say 2020. So I've desynchronized these two clocks. So now if I jump into the wormhole from the Earth and I come over here, when I arrive in Alpha Centauri, instead of being 2025, it's now 2020. So I've kind of, in a sense, gone backward in time, right? And of course, in that sense, it doesn't really physically matter because I was never on Alpha Centauri, right? I've not been involved with the past history of Alpha Centauri at all, so my being there at some earlier date on Alpha Centauri's clocks really doesn't really matter. It's kind of like going to if you went to another country and they said when you showed up there, they said, well, we're using a different calendar, and it's a different year compared to when you came. It'd be like, well, that didn't really matter for me because I was never here to experience any of this stuff in your country on this other time scale anyway. So in that sense, arriving early in time, although it sounds strange, doesn't really impact anything. But if I now get here in the year 2020, and instead of going back through the wormhole to get back to the Earth, suppose that I now travel along the surface of the balloon, or the surface of the ball, and I stay in normal space, and I go at a very high rate of speed all the way back around. It's possible for me to go less than the speed of light and go all the way back around and get back to the Earth in less than 5 years, right? In which case I arrive back at Earth before the year 2025, right? And I'm able to arrive back at Earth before I left, in that sense. So I've been able to make a closed time-like curve by doing this, right? So I can arrive back and see myself as I'm leaving, right? If you're able to make these exotic materials, remember, right? Right. So this is related to what you're going to be seeing in the movie. Now, in the movie, they don't get into the details of how they're making people go back in time, but the question comes up is, if you can go back in time, what does that mean as far as causality goes, right? So this possibility of backward time travel really messes with our idea of causality, right? So suppose, for instance, suppose you jump into the wormhole, you arrive at Alpha Centauri, and you bump your head. When you get there, and you leave a scar on your head, right? And then you travel back around, and you get back at Earth, and now you meet up with the younger you before you leave, and here's this older you arriving with a scar on your head, and the younger you is about to leave, and maybe you stop the younger you from leaving, right? Maybe you grab the younger you and say, no, I'm not going to let you go, right? Then what happens to the scar on your head and all the other events that happen to you along the way, right, during that whole trip, right? And so you end up with these sort of paradoxes that happen, right? And which also comes up with this idea, again, of free will, which this movie is going to be dealing with this idea of, and does that mean that somehow that if I tried to do that, right, if I'm able to do this and go back in time, that nature is going to somehow stop me? Even though I want to do that, suppose I want to go back and stop myself from going, will something prevent me from doing it because nature won't let me stop, right, won't let me make a paradox that this isn't self-consistent in some way? And in fact, this is what Stephen Hawking believes this so strongly that the universe won't allow this, that he published a paper about something he called the chronology protection conjecture, right, where he didn't prove this. This is still an open question for debate, but he believes there's a lot of evidence to say that the universe won't allow these closed time-like curves, that there will always be something that will happen, some physical phenomenon, that anytime you try to go and make a curvature, a situation where you're going to be able to make a closed time-like loop like this, that nature will prevent that from happening. Right, so some more important features then, things to keep in mind that we've learned, right, is that so backward time travel is possible if you have these exotic materials, in which case you form this closed time-like loop, right? And that nature might not allow that, though, right? If Hawking is correct with his chronology protection conjecture, right? And that's still, again, an open question for debate. Right, so some things I recommend as far as reading goes. There's some really great books out here, sort of the popular science kind of level. This is a really great one. I enjoyed reading this as I was prepping for my talk by Richard Gott, Kip Thorne, Paul Davies, and Lee Smolin. There's a lot of others who've written some great books about this. I want to thank OMSI and the Perimeter Institute. These are the folks that came up with this idea of the curved space-time demo, right? So I really want to thank them. Pacific University, and all of you for being here. I really appreciate that and the opportunity to be here and talk to you about this. So, and remember that traveling through hyperspace ain't like dusting crops, boy. So it's what Han Solo says anyway. Thank you. So any questions? The question is, right, how do we know the difference between a big, so right now we believe the universe is expanding. There's like evidence the universe is expanding. And there have been models that say, well, eventually if there's enough mass, that the universe will slow down its expansion rate and eventually turn around and collapse back on itself into sort of a big crunch or the reverse, right? So a couple things about that. So one is that our current understanding now is that actually that there's a lot of evidence that the universe is accelerating actually its expansion. It's not slowing down. It's actually speeding up in its expansion, right? So the universe is getting bigger and bigger at a faster and faster rate now. And so we actually don't really believe at this point that the models the data actually indicates that it's never going to slow down and turn around and come back. But there was a lot of that's very recent that's been the sort of understanding, right? So it wasn't that long ago that we thought, well, it's possible it's going to turn around and come back into a big crunch, and what would that look like? Now, of course, it takes remember that the information can't travel faster than the speed of light, right? So it's possible that maybe if that was to happen, that some galaxies somewhere have started to turn around, the universe starts to recollapse. We won't know about that for a long time because it's going to take the light from those galaxies to come to us, right? A long time to do that. But I guess presumably right now, right, things are, the reason we know that things are receding away from us is that the light from them is shifted to a different color than what we normally expect, right? So it's what we call the red shift. So everywhere we look, the galaxies around us are all the wavelengths that they emit, that the atoms of their stars emit, is all shifted toward the red, which tells that they're moving away from us. And so if it was all moving towards us, they would be shifted toward the blue part of the spectrum. So we would see this sort of blue shift of all the light. That would tell us that it's all moving towards us instead of all moving away from us. Right? And then there's all sorts of other interesting questions then about also, we think of if during if the universe was to turn around and have a big crunch, we think about what this means in terms of entropy, things like this. What gives us our sense of a flow of time is often is this idea of an entropy order, that things move from ordered states to disordered states on average, right? So like if you run a film backwards, if you imagine setting up a triangle of balls like you're going to play pool or something, and you take a movie of the cue ball coming in and breaking those apart. If you take that movie and run it backwards, you see a bunch of scattered balls all come together and form a triangle. That would seem strange, right? Because we never see that happen, because that gives us sort of an idea of the flow of time, that things move from ordered states to disordered states. But there is some conjecture that if the universe was to turn around and start recollapsing instead, that would, in that case, would the order of time also reverse, right? The thing would start to move towards a more ordered state, and our sense of time flow, in a sense, would end up being reversed of what it is right now, which is sort of an interesting thing to think about. And would we even know the difference, though, right? So if you live in a situation where things are always moving, what we think of now is backwards in time, but we always live that way, then for us that would be kind of forwards in time, right? So it's only if you can compare between two regions that have their time orders reversed to each other that you would actually be able to tell that there's something weird going on. That's a good question.
So you are saying that what we see expanding away from us,
yes,
is the light that's telling us information from tens of thousands of years ago,
millions of years ago.
When in fact it could be collapsing.
Yeah, that's true. Conceivably it could be. Like it is theoretically possible, right? That if those galaxies that are a billion light years away from us have turned around and started coming back, right, at this moment, in a sense, right? Because we're seeing the light from them as they looked a billion years ago, right? So if they right now at this moment are coming towards us, we wouldn't know that necessarily for another billion years, right? Because it takes time for that light to come back towards us. That's right. So we're never seeing those objects as they are in this moment, in a sense. We're seeing the light that left them, however long it took for the light to get back to us. Yeah, so we can't say exactly what they're doing in this moment at this time. But given all the information we have from looking at in all different directions at lots of different stars and galaxies, then we develop models, right, based on trying to make things self-consistent, right, with the way we know how our star behaves and things locally here behave, and the information about all around us that we see this redshift everywhere, and other types of information like that. Then we kind of build these self-consistent models to help us understand and give us a good idea, at least to predict what we think is happening. We may be wrong, right? But that's our current state of understanding is that. But we're always open to, we could be wrong about that. Question, yeah. Yeah, okay, so the first question was like, what is our current model of, so we said the ball geometry is not the correct geometry for the time, the curvature of time near the surface of the Earth, or even near like a large object like a black hole or something, right? So black hole is just, the curvature, the shape is not any different than near the Earth. It's just a much more massive object, right? So the question is, what is the correct geometry, or what we think is more of a inverted, like a funnel kind of a shape in a sense, right? In a sense, so that way, if you imagine having a funnel this way, right? Then then instead of the ball geometry, it starts out wide and gets tapered up to the top, which is why Alice measured a shorter time than Bob did. But if it was the inverse of that, it was more of a funnel this way, then Bob would measure a shorter time and Alice would measure a longer time, right? So that would be sort of a closer, at least mental model of that, right? Would be this sort of thing. It's actually mathematically it's like a hyperbolic kind of a shape, but that's sort of this sort of funnel. As far as the difference between a closed time-like loop and an open thing, right? So I guess hearing your question, so a closed time-like loop is any time you have a world line like me, right? My world line is all the events that happen to me as I go through my day, through my life, right? You can map all those out in their position and time coordinates. And if at some point, if that is able to eventually, just by me following, just moving through time, because that's all I can do, right? Nature says you must move onward through time. If that world line eventually wraps around and reconnects with itself, right, then that would be this closed time-like loop, right? And at that point, if that ever happened, then you'd have this weird situation where I would, maybe meet with myself at an earlier age or something like that, right? We believe right now that there aren't such things, right? And that so all of us have more of an open world line in a sense, right? They don't form closed loops. So it follows some sort of a twisty, windy path through the curvature of space-time, but it never loops around and reconnects with itself, right? So it just keeps sort of flowing onwards and onwards, but never wrapping around and forming some, any sort of a reconnection with itself.
So basically, if you go back in time, you have to, if it is possible to go back in time, it has to form a closed time loop.
Basically, that's right, yeah. So if you're going to go backwards in time, then your world line has to form a closed time-like loop, right? So because you're going to end up going back to a place and a time where you are, again, sort of meeting with yourself, right? You are in that same position, time, location twice, right, at the same moment, right? So once after having already gone forward in time, you then meet yourself at an earlier time. So your world line, in a sense, has to reconnect with itself. That's right. Yeah. Yeah.
So if I were to hypothetically go through a wormhole, and for some reason I was very bored of Alpha Centauri.
Yeah. Because they're very boring people in Alpha Centauri. Yes.
Yeah, absolutely.
Uh-huh.
Could I go through another wormhole back to Earth and arrive at an even earlier time than if I just followed the regular path of travel?
Interesting, right? So you're saying let's see if I go back to this picture, see if I can think my way through this a little bit. So yeah, sorry, I'm going back in time right now, right? That's right, we're forming a closed time-like loop. Now I have to start saying exactly what I was saying a little while ago or something, right? So you're saying, is it possible once I jump in here, right? So now I jump in here and I arrive at Alpha Centauri, and could I now maybe find another wormhole that reconnects me back here to Earth, right? At an even earlier time, that kind of thing. That is a good question. Yeah, so if you arrived here at, say, 2020, could I then jump into another one and arrive back here at 2015? I don't see why not, I suppose. If you have enough of this exotic material laying around, right, to form more wormholes, then you could probably form all sorts of wormholes between all sorts of different times in that sense, right? Yeah, as long as you have enough of that, I would imagine. That's my guess anyway. Just to give you an idea, in Kip Thorne, actually in Gott's book, he talks about this briefly, and he was quoting Kip Thorne, who's one of the world leaders in this area, right? He's sort of one of the minds behind Interstellar and stuff, right? That to make this sort of a wormhole would require something like 200 million times the mass of the sun worth of exotic material, right? Something like that. So it's not an insignificant amount of stuff that you got to make. So yeah, so something like, galaxy sorts of size amount of stuff. But yeah, but since we're just talking hypothetically, then yeah, we might be able to do that. Is there anything in the universe that's moving towards us? Yeah, that's right. So that's right. No, that's true. I did say that. So on average, right, when you look at all, there's of course millions of galaxies, and on average they're all moving away from us. Now, actually, our nearest galaxy neighbor is Andromeda. Is moving towards us. It's not moving away from us, right? In fact, it's going to collide with us someday. Actually, about how long time? 4 or 5 billion years. About 4 or 5 billion years from now. So if you want to hang around for that, then Andromeda will be colliding with the Milky Way galaxy. And so yes, it's moving towards us on a collision course right now. So yeah, not everything in the universe is moving away from us. But if we look at the on average over all degrees, all possible ways you can look outward, then the vast majority of things are moving outward away from us, of all the galaxies, not moving towards us. Right. All right, that all we have time for? Okay, so yeah, so enjoy the movie. Thank you very much.